Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 6.2.3. This is called Identifying Similar Shapes. Have you ever noticed how many different kinds of cell phones there are? Sometimes you might have a cell phone that is similar to one of your friend's cell phones because it is the same brand, but it might be a different color or a different model. Occasionally, two people will have the exact same cell phone, including brand, model, and color. Sorting objects into groups based on what is the same about them is also done in math. As you work today to sort through some shapes, ask the following questions or think about the following questions. How do the shapes grow or shrink? What parts do we compare? And how can we write the comparison? All right, so let me just back up a little bit here. There is a form on the Google Classroom that looks like this. And if you have the ability to cut it out, go ahead and do that. This is an activity that generally takes a fair amount of time to do in class. And back in the days when I was able to teach my classes for 90 minutes, we would be able to take and cut out each one of these and compare them, comparing the corresponding sides and the corresponding angles to determine which ones were similar, which ones were congruent, and which ones are neither, okay? But that does take up time, and we're just not able to do that right now. The second process that I had students go through when trying to answer these questions involved tracing on very thin, what we call patty paper or tracing paper. And that's why you see this kind of discolored kind of a square here. And that you would take your piece of tracing paper, set it over a shape, and then go ahead and trace that shape, and then move over to some of the others and compare the shapes and the sizes of the various images there. Excuse me. So we're just going to try and make this work. If you do not have printer capabilities, you can just watch what I'm doing here. If you do have a printer and you want to print this off, I would probably recommend just cut out the original shape and use that as your guide, similar to what I'm doing here. I'm not going to go ahead and superimpose these shapes onto the tracing paper at all. All I need is the original on the tracing paper. Okay. So these directions say carefully cut, but you don't necessarily have to do that. It says decide how each shape is related to the original shape. Okay. Then it says compare the angles and the sides of shapes A through G. And ultimately what you want to do is this. You want to make a list of all the shapes that are similar to the original shape and which ones are not similar. Okay. So please do that right now. Please take a little bit of time to, if you're going to print this out, go ahead and print it, cut out that original shape, and put it over the top of each one of these images, A through G, and then make a list of which ones are similar, which ones are not similar. And actually, once you go ahead and identify, because there is a question that's going to come up, are there any of these shapes that are congruent? Okay, remember our definition of congruent shapes. They're the same size and the same shape, meaning that all the corresponding sides are the same length or same measure, as well as the corresponding angles. If they are similar, like I'll just go ahead and show you right here, the similar shapes have corresponding angles that are the same. So the right angle is the same, this obtuse angle is the same, the acute angle at the top is the same, and the acute angle in the bottom right-hand corner is the same. So shape B is definitely similar to the original, but it's not the same size, so it's not congruent. Okay, so take a little time doing that, and then we will do our reveals. Okay, I'm going to pause. You go ahead and pause and make that list. Okay, what did we find out? Well, first of all, we might have to do some rotations. Right? So I'm going to rotate this, and you notice how, oops, stop it. Looks like everything is perfect there. So figure A is exactly the same size. So this is not only similar, but it's congruent. We already determined B was the same shape. Now let's look at C. Do we get the angles matching up perfectly? Yes, they do. So C, A, B, and C are all similar. Now we got the right angle, but you see that angle right there in the left-hand corner? It looks like figure D has a wider angle there. And looks like the angle at the top is not as wide. So we're going to go ahead and say D is not similar. Let's rotate this guy around to see if, oops, stop it. If E looks good, yes, 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 and yes. And then let's look at F. Yes, 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 and yes. But then you look at G, let's get our right angles together. And you can see this angle is okay, but this angle is not. So my conclusion is that shapes figures A, B, C, E, and F are all similar because their corresponding angles are congruent, even though the corresponding sides are not necessarily equal. Okay? And then the two that are not would be angle D, or I'm sorry, figure D and figure G are not similar. All right, shapes that are similar do not grow or shrink. Or shapes that are similar that do not grow or shrink are called congruent shapes. Okay, so did we all agree that A was the one that was congruent because it was the same size and the same shape? Yes, it is. Okay, so now we've got a whole new set of shapes down here. Let me go ahead and get you out of there. All right, record the pairs of shapes below that appear to be congruent to each other. So you got triangle A, B, D, F, and G. Then you've got quadrilateral, or actually they're parallelograms, aren't they? C, E, and H are parallelograms. And we are trying to find which ones are congruent to each other. So we're looking for the ones that are exactly the same size and exactly the same shape. Okay? So it says, get a piece of tracing paper for your teacher and use it to check. Okay, well, same idea here is you're probably not going to be able to do it. And unfortunately, I do not have a resource page for you to print out to do what we did on the previous example. So we're just going to have to watch the video or just look on the screen and see if you can figure out which ones are exactly the same. Now, I decided I was going to throw these three symbols in. You might want to write these down because in geometry, we use slightly different symbols to represent phrases that we use a lot in geometry. This little wave kind of here kind of looks like a reflected sideways S, means is similar to. Okay, think of it as just a single wave. If you've got that single wave over top an equal sign, this means is congruent to, which is the geometry term for is equal to. Okay, we don't like to say that this angle is equal to that angle or whatever. We say is congruent to. Don't know why, but that's the language that we use in geometry. And then these three dots that form a triangle is the shorthand for the word therefore. Okay, so looking around, we're looking for congruent shapes. So when I look at triangle A, it looks like it could be a right triangle, but it looks like it's a little bit more than 90 degrees here. Are there any other triangles that appear to have a right angle? No, that's not it. No. So A doesn't have anything that it is the same size as. B is clearly a much smaller triangle than any of the others. So that wouldn't have a matching partner. D does look like it might have a matching partner in G. So what I'm going to do is I've gone ahead and I've traced over that. And now I'm going to come over here and I'm going to rotate this guy and see if this will go completely over top, and it does. So we can make a statement that says that triangle D is, or figure D, is congruent to figure G. We just had to reorient the triangle. Now let's take a look at C. Are there any other parallelograms that look like they're shaped like this? No, E and H are not as stretched out as C, so that wouldn't work. And then you look at E, looks like it's matching up with H, right? So let's go ahead and see if we can rotate this guy around and see if we can get them perfectly matched up. that look like they're going to be perfectly? Yes, it does. So E and H appear to be congruent to each other. So I'll make those statements. We'll say that figure D is congruent to figure G because they're the same shape and the same size, as well as E and H are congruent to each other. Now, are there any others any other statements that we can make? Now, this is not a part of the directions. They were just asking for congruence, but I was just kind of curious. Let's look at how D compares to F. It looks like that angle is the same, this angle is the same, and this angle is the same. And if I were to stretch this guy out, then there would be some congruence happening here. Yes, it is. So we can say that figure D and F are in fact similar to each other, even though they're not congruent to each other. And then that makes me think, well, what about B? What if I were to shrink it down? Could I get B to be the exact same? So shrink it down a little bit. Yes, that looks to be the same as well. So we could say that figure D is similar. Wait, did I have one of them or did I have two of them? Oh, that's supposed to be only one. Sorry, there we go. It's supposed to be one. So D is similar to F, and D is also similar to B. Therefore, what statements can you make about triangles B and F? They must also be similar to each other. And of course, let me go ahead and get rid of that because that wasn't the right symbol. There we go. Here I'm using the congruent symbols, the similar symbols, and the whole therefore. We're drawing a conclusion. And it's kind of like, if you think about this with the equal values method, if D is similar to F and D is similar to B, then F and B must also be similar to each other. So this is some information I would like for you to get recorded, and there's a good chance that this is going to show up in M&Ms, but if they're not, please get it written down. If they do show up, then there'll be less that you'll have to write for your M&Ms later on. Congruent shapes. All corresponding sides are going to be equal to each other in length, and all the corresponding angles will be equal to each other in measure. So you can see this triangle is identical to this triangle. This pentagon is identical in size and shape to this pentagon. When you're dealing with similar shapes, the angles are still equivalent to each other, right? The corresponding angles are congruent, but the side lengths are not necessarily the same length. However, they are proportional according to a scale factor. So if I were to take this, does it look like how many of these could I fit in there? 1, 2. Does that look like, I guess they're not perfectly the same. So my scale factor would not be perfect. So I don't know what the scale factor is, so I'm not going to be able to make any statements about proportionality and length there, but we do know that the corresponding angles are the same. It's just the lengths are a little bit different. Okay, so congruent shapes, these are examples. Similar shapes, those are examples. All right, so Quan enlarged shape Q to make shape P below. Are his shapes similar? And so if they are similar, you should notice that the corresponding angles appear to have the same measure. But one other piece that is really important to note is the fact that when you have similar sides, that means that the corresponding sides are proportional in nature. And there's a scale factor that you can apply. So taking a look at these two shapes, notice how shape Q has a side length here that is 5 units and P is 10 units. That makes it appear as if our scale factor is equal to 2, since we are going from the smaller to the bigger, right? If we were going in the other direction, from P to Q, then your scale factor would be 1/2. So it just depends on whether you're getting bigger or getting smaller. These will be reciprocals of each other, okay? So I'm going to go ahead and take a look at this. I've already filled in the numbers here. This is 10 units, this is 6 units, this is 6 units, this is 2 units, and this is a diagonal, which we'll figure out later on what the length of that is. This is 5, this is 5, this is 3, this is 3, this is 1. So does it appear as if all of our corresponding sides follow with that same scale factor? And it certainly does appear to be the case. So we can state that the shapes are similar and the scale factor is 2. All right. Using the triangle shown at the right as the original figure, predict which of the scale factors below would enlarge or reduce the shape. Okay, so these are considered scale factors. Some of them are greater than 1. Some of them are less than 1. So which ones would make the shape bigger when you multiply? Say, take this side right there. It doesn't matter. They're both 12, right? If you multiply times the scale factor, will that number get bigger or smaller? Will this side length get bigger or smaller? Okay, go ahead and take a few moments to determine which ones would make it bigger and which ones would make it smaller. All right, now what we have to do is we have to look at these fractions and determine which ones are greater than 1 and which ones are less than 1. Since 5/3 is greater than 1, that means that the product of 12 and 5/3 is going to be greater than 12, the number that you originally started with. So we will just multiply. Remember, you multiply numerator times numerator and denominator times denominator. So we'll give these 12's a denominator of 1, and 12 times 5 is 60. 1 times 3 is 3. 60 divided by 3 is 20. So after applying this as your scale factor, this side length and this side length would both be 20 units instead of 12, which would make it bigger. When you take 12 over 1 times 3 over 4, you end up with 36 over 4, which is 9. So in this case, because 3/4 is less than 1, you're going to get a figure that is shorter. This would be 9, this would be 9. So the entire figure is going to be smaller than the original. Here you're going to have 12 times 7 is 84, and 1 times 6 is 6. So 84 divided by 6 is 14. So the 12 units becomes 14 units, which makes it a bigger shape. And then the last one, since 2/3 is less than 1, it should make it smaller, correct? So 12 times 2/3 is 24/3, which is 8. So yes, absolutely. When you multiply each one of these side lengths times a scale factor, that is 2/3, you're going to get a smaller number, a shorter side length, so you'll get a smaller figure. So what do we take from this? Nothing really that I haven't stated before, but it is absolutely essential that we understand this. If the scale factor is greater than 1, your new shape will be bigger than the original. If the scale factor is less than 1, and when I say less than 1, I'm talking about the absolute value, right? So a scale factor between 0 and 1, you're going to get a new shape that is smaller than the original. All right? All right, so this is the last lesson, I believe, of this week. Possibly not, depending on the timing of the year. But we should have an assessment coming up and possibly even a check for understanding. So let's move on to the next activity before we get into our homework. All right, take care. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood. Feeling